Okay, so in the last lecture, we had talked about the different reactions that happens when you go, garnet forming reactions that occur when you go from low pressure granulites to high pressure granulites. So essentially, looking at other way, if you go from the upper part of the crust down to lower crust part of and the mantle, you would expect these reactions to happen, by which low pressure granulites are transformed slowly to through garnet forming reactions to garnet granulite phases. But in all the reactions that we have considered, there is a great simplifying event. We have only considered anorthite in the plagioclase, and that is not a very good way of looking at things. Why? I will tell you. Say, for example, if you have a reaction, orthopyroxene plus anorthite is equal to garnet plus quartz. Let's say that is what is being happening. If you have this reaction, then let us look at it. What happens to let us look at it, at what happens to the plagioclase. Say, for example, this is an orthopyroxene crystal with this prismatic cleavage, and this is surrounded by, say, plagioclase. Now you know that across the amphibolite to granulite phase transition, the plagioclase composition is oligoclase andesine. This is what I told you before. Generally oligoclase andesine. Andesine labradorite, that range, it's not so often formed, for the simple reason that hornblends are never pure Schermakite. You know, in the Schermakite breakdown reaction, you only produced anorthite and no plagioclase. So that does not normally happen. So at the highest grade, your hornblends are pergosite Schermakite solid solution, and so the plagioclase that you get have a composition of roughly andesine, end of andesine, beginning of labradorite, and that is it. You don't get pure anorthite, So this plagioclase that you have here, this is not anorthite. This has the composition of roughly half andesine and a little bit of labradorite. So essentially, this plagioclase contains calcium and sodium. Now, when orthopyroxene, as you can see, if orthopyroxene is reacting with the plagioclase and is forming, say, garnet coronas with quartz in it. Remember, we had quartz plus garnet, so we have quartz blebs normally in these garnets that form. So what happens, it is extracting this calcium component, an anorthite component, reacting with this plagioclase, and this calcium goes in to produce grossula in the garnet. Okay? This calcium in the plagioclase is taken into the reaction, and you are producing the grossular component of the garnet. And the magnesium iron content of the garnet is delivered by the composition of pyroxene. So in this plagioclase, in this space around orthopyroxene, two things are happening. One, the proportion of plagioclase is decreasing. And the composition of the remnant plagioclase. Have you understood? That means the proportion of plagioclase near the garnet boundary, this is now becoming more analytic. So what happens in these plagioclases, the Na by Ca ratio, that means albite by anorthite, or the albite content of plagioclase increases towards the garnet. So normally, the plagioclases that surround the garnet are typically zoomed. So these are high calcium, and as you come in this plagioclase closer to the garnet, they become albitic. So plagioclases are strongly become zoned. So when you are producing this garnet, by extracting the anorthite content of the plagioclase, your plagioclase is becoming more and more albitic or sodic plagioclases. So in many outcrops, in many sections, in fact universally, such type of garnet formation is associated by increase in the albite content of the plagioclase towards the garnet corona. This is a very common feature observed in all granulite terrains. So that means taking the anorthite molecule of plagioclase in isolation, excluding the albite component, is not a good way of looking at things. You have to find out a mechanism by which you extract anorthite, you take the anorthite content, but you need to demonstrate that your plagioclase that you produce is more albitic. I will try to show this what happens. It's not very easy for me because it involves a tetrahedron. I will take a tetrahedron which is Na, Ca, FeMg. I am not making any difference between magnesium and aluminium. I take this tetrahedron, NaCa, MgFe together, and aluminium, and of course you have plus SiO2. I have not taken the oxides here, I have taken elemental abundances. Now let me try and draw this diagram for you. It's not very easy for me to draw because it's perspective drawing, and I am no Leonardo, no Picasso. So this is sodium, this is calcium. Let's say NaCa, let's say this is aluminium, and this is magnesium by iron. Okay? Plus Si. Plus Si. So orthopyroxene should plot here. This should be the position for plotting of orthopyroxene, right? Because it does not contain aluminium, it does not contain sodium, and it does not contain calcium. And diopside will only contain CaMgFe. So diopside occurs here. So this is orthopyroxene, this is diopside. Have you understood? Now you see albite. Where does it plot albite? See, the formula of albite is NaAlSi3O8. Na is to Al is 1:1. That means here, this will be the position of albite. Yes or no? 50-50. What about anorthite? CaAl2Si2O8. So CaAl2, 1:2. So that means it will be richer in aluminium. So CaAl2, here you see, this is Al and CO2. If we divide it into 3 parts, then CaAl2, this will be anorthite. CaAl2. So this is the position of albite.
So won't it be towards the Al and Al?
Yes. Right. This one will be anorthite. So your albite should your plagioclase composition should lie here. On this space, so NaCaAl, this should be the face. And this should be orthopyroxene, this should be diopside. Now we look at grossular, Ca3Al2. So that means out of this is 5. So Ca3Al2 will be 60%. Ca3Al2 will be 60%. So grossular and more will be Ca will be more. So let's say this is grossular. A little bit away on the edge, Ca3Al2 on this point. Where will be pyrope? Pyrope will be, remember, Mg3Al2. So again, like grossular already derived. This will be Mg3Al2 will be the same 3 by 5, that means 60%. So this will be somewhere, this will be pyrope or almandine if you want. And your garnet composition then should be lying on this point. This is the tie line on which your garnet composition should lie. Am I right? So this should be the grossular and this should be pyropalmandine on this. What is the reaction? Orthopyroxene plus plagioclase. Okay, let us do one thing. In this diagram, the plagioclase close to garnet should be albitic, isn't it? That is what I said. So let's say we write, this is plagioclase 2. That means the product. So where is plagioclase 1? Somewhere here in the distance. So that's plagioclase 1 and plagioclase 2. So now what we can do is we can write OPX plus plagioclase 1 is equal to garnet plus plagioclase 2. Where plagioclase 2 should be more sodic. This should be Na rich and this should be Ca rich. This is what will happen. So if we take an orthopyroxene and react it, you can see this is grossular, and this is your albite and this is an orthite. So if you take orthopyroxene, it's difficult to draw in this perspective, very difficult to draw. Let's say my orthopyroxene plagioclase 1 is here. This is plagioclase 1 orthopyroxene. Have you understood? Orthoclase 1, OPX 1, plagioclase 1. Now, if I have to then get a garnet, then these two tie lines should cross cut. So let's say if you have a garnet here, then the plagioclase should be, plagioclase 2 should be here if your garnet is here. Because if this is plagioclase 1, which is calcium rich, then plagioclase 2 should be albite rich. So your plagioclase 1 plus orthopyroxene gives you garnet plus plagioclase 2. I'm hoping that these two tie lines intersect at a point, in which case the compositions can be balanced. So once again from the tetrahedron you see that if I take an orthopyroxene and plagioclase 1, if you produce a garnet, then if it has to cross cut this tie line, then your plagioclase 2 must necessarily be more sodic. Same thing will happen, say for example, if I take dioxide. Say I take dioxide and plagioclase 1. Now you see we'll have a problem. Your garnet composition, to tie line it, you have to have a composition here and you have to have a garnet composition here in order that these two intersect. But whether it is intersecting or not, the plagioclase 2 composition should be more albitic. It has to be higher. You can't have a plagioclase composition lower than this because the two tie lines would never intersect. So that is something that is very important. If you take the system as NaCa, this system, even this system is wrong because you have clubbed magnesium and iron. So it should be even more. And I will tell you how it is done in possibly in the next video lecture. Actually, this is not a 4-component system. It has been clubbed as a 4-component system. It's a 5-component system. And imagine if I had so much problem drawing a quadrilateral or a tetrahedron, how much problem will I have if I have to draw a pentahedron? And then to visualize the crossing tie lines. It's almost impossible to do. But what I wanted to impress upon you, that it is always said orthopyroxene plus anorthite is equal to garnet plus quartz. You will see it in every book. But the real question is, what happens to plagioclase? The proportion of plagioclase decreases because and the composition of the plagioclase becomes more sodic. Plagioclase 2 is more sodic than plagioclase 1. So all plagioclases show a strong zoning towards more sodium-rich composition next to garnet. So that is an important aspect. So one thing is, you can imagine, if I am going on producing garnet at the high pressure granulites, then I am making my plagioclase more and more sodic. Do you understand? So high pressure garnet has more sodic plagioclase than low pressure granulites. High pressure garnet bearing granulites have more sodic plagioclase than garnet free low pressure granulites. For this simple reason, that if you take the anorthite molecule and produce the grossular component of garnet, then the plagioclase composition should become albitic. So this is for you to realize at the point of time that as you get into low pressure granulites, orthopyroxene, clinopyroxene, plagioclase, no garnet, 2 high pressure granulites, garnet, 2-pyroxene, plagioclase assemblage. So you not only produce garnet, you also make your plagioclase more albitic at the higher pressure. So your plagioclase becomes more albitic at higher pressures, and that is why it becomes stable. So now when you have the plagioclase at high pressure, this is what happens. So your plagioclase contains albite, NaAlSi3O8, and CaAl2Si2O8. Your plagioclase contains both, but there is a dominance of albite. So what happens now, this plagioclase, it breaks down to NaAlSi2O6 plus SiO2. This is what happens. NaAlSi2O6, this now is in the octahedral side, and this now is in the tetrahedral side. And this mineral is jadeite. This mineral is jadeite. And if you take the anorthite component, then you have CaAlSi06 plus SiO2. Again, this is the octahedral side and this is the tetrahedral side. So this is called calcium Schermax molecule. Calcium Schermax molecule. And this is jadeite molecule. Remember, your high pressure garnet is dominated by albite relative to the low pressure garnet free granulites. This is proved. So essentially, if you take more albitic plagioclase, this plagioclase breaks down to jadeite plus quartz, and this anorthite breaks down to calcium Schermax plus SiO2. So now what happens? What was your original composition of clinopyroxene? CaMgFe Si2O6. Yes or no? this was tetrahedral side, this was octahedral side, and this was fourfold side. Now what you get is NaCa AlMgFe AlSiO6. This is the clinopyroxene that you get. What was the low pressure clinopyroxene? This was the low pressure clinopyroxene. But when your plagioclase breaks down into jadeite component and calcium Schermax component, then you have this type of a formula where you have NaCa in the octahedral side, aluminium, magnesium, iron in the this is the cubic side, AlMgFe in the octahedral side, and aluminium and silicon in the tetrahedral side. This is what is called omphacite. Essentially, omphacite is jadeite bearing clinopyroxene. Essentially, your omphacite is jadeite bearing clinopyroxene, or omphacite is a sodic clinopyroxene. Why does it become sodium rich? Because of the breakdown of the albite molecule of the plagioclase. Albite molecule of the plagioclase, and also the Schermax molecule of anorthite. So this is what is your omphacite. So now then, remember I showed you the first diagram in virtual lecture 29, where first orthopyroxene breaks down and then plagioclase out. That determines the eclogite facies. So that plagioclase out reaction is this. Jadeite, albite is equal to jadeite plus quartz. That is your plagioclase out reaction. So then what you get is now, you get clinopyroxene, you get omphacitic clinopyroxene, plus CaMgFe whole thrice, Al2Si3O12 garnet. That is your assemblage, plus quartz. No plagioclase, no orthopyroxene. No plagioclase, no orthopyroxene. This is the classic case of orthopyroxene out. How does orthopyroxene get out? Remember the reaction 3, orthopyroxene plus plagioclase. That's how orthopyroxene goes out, and it produces albitic plagioclase. Albitic plagioclase albite component breaks down to jadeite. This jadeite mixes up with the original composition, and so you have omphacitic clinopyroxene, which is nothing but a sodium-rich dioxide. And if you have sodium-rich dioxide, you will get aluminium because of the Schermax molecule. What happens at the gabbroic, at the eclogite, at the granulite-eclogite transition boundary? Right. Now what happened? There is so if I go down pressure now, there was a talk several years ago, more than half a decade ago. If you have a crust, and then you have the mantle, and then you have the mantle, and then you had the moho. And in those times, there was a boundary between what is called Sial and Sima. Do you understand? Sial and Sima. So, previously there was a discussion. This discussion is no more there today. There was a lot of debate about what is the nature of moho. What is the nature of moho? People thought that the mantle was composed of eclogite. Have you understood? The mantle was composed of eclogite. What is eclogite? I just told you. Omphacite plus clinopyroxene. Omphacite plus garnet. there is a name for this garnet. It is called Grospedite garnet. Grospedite. The name is very simple. It's grossular pyrope-rich garnet. Grospedite. So omphacetic clinopyroxene and grospedite garnet. This was the assemblage of the eclogite. So people thought that this Morovicic discontinuity that it was because of an eclogite. And the rocks above it were sima or mafic rocks. And what were the composition of mafic rocks? Maybe some gabbros. So which contains OPX, CPX, plagioclase. That is what is a normal gabbro, norite. You will have orthopyroxene, clinopyroxene, plagioclase, and then omphacetic garnet and clinopyroxene. So people thought that this boundary of Moho was essential. Look at this, low pressure granulite, orthopyroxene, clinopyroxene, plagioclase, low pressure granulite, to eclogite. So what people thought this Moho was, it was a gabbro eclogite transition boundary. Gabbro-eclogite transition boundary. That is what was there in the mind. Let's not go into names who coined this and what is it. But this was, even if you go to the internet and ask for things, you will see that there is called the gabbro-eclogite boundary. What does this mean? It means that the composition of the sima, which is a basalt, and the composition of the mantle, which is an eclogite, which is also the composition of a gabbro. So essentially the Moho is not a chemical boundary, but a boundary for physical transformation of minerals. Have you understood? So it was thought to be as phase transition boundary. Phase transition boundary means OPX, CPX, plagioclase, OPX, CPX, plagioclase, this was the gabbro, and the boundary was CPX garnet. So this was, there is no chemical difference between the sima, between the gabbros of the sima or the basalts and the mantle, which was an eclogite. So there is no chemical difference. So the Moho was essentially a phase change boundary. This was the debate. The other part of the debate was people or the geophysicists used to take the stand that Morovicic discontinuity is not a phase change boundary, but a chemical discontinuity. It's a chemical discontinuity. One set of people thought there is no chemical discontinuity, and the transition is because of the transition of the mineralogy, OPX, CPX, plagioclase to CPX garnet. No chemical change. The other people thought that no, the boundary between this, the Morovicic discontinuity, is a chemical boundary. Is a chemical boundary, and this debate went on for quite a while. But slowly what happens, so essentially one was talking about whether the Morovicic discontinuity was a chemical boundary, a boundary where chemistry of the rocks changed, or whether the chemistry did not change, the transition changed from 2-pyroxene plagioclase to clinopyroxene garnet. There were a lot of laboratories in which a lot of experimental work was done, but one of the most famous laboratories that addressed this very important issue at that time were two very famous scientists, a teacher and a student combination. One was A.E. Ringwood and D.H. Green. These two people. Ringwood was the professor and D.H. Green was his student. So Ringwood and Green, they worked in the Australian National University, ANU, very famous experimental technology lab at that time, And they worked in a laboratory called RSES, Research School of Earth Sciences, Australian National University Research School of Earth Sciences, where these two people set up fantastic laboratories. And they did a lot of experimental work. Many of it, a vast majority of it, related to gabbro-equinoid transition. These were hard experimental data. So we will now talk about what was the importance of this experimental work. They did a lot of experiments. For me, it's not important that I tell you a lot about all those experimental data. At that time, it was taught to us in great detail. Now it has sort of lost its importance because now we know that the monophasic discontinuity is the chemical boundary. It has got nothing to do with the physical change. But that came through a lot of hard work put in by very famous people. The other famous laboratories I should mention before I go into Ringwood's work was the Carnegie Institution of Washington Laboratory. It was another very famous laboratory that contributed greatly to our understanding of the mantle. Now here is an experimental work. The rock was, I will tell you, let me first draw it, quartz foliite. The rock was quartz foliite. Experiments were done at 1100 degrees centigrade. So here is the result of the experiment. Sure. This is a phase diagram to remember. This was only one of the many experiments that they did. These experiments were done in quartz tholite. They did experiments in almost all conceivable mafic rocks. I will give you a summary diagram in a moment once I finish this. But this diagram is very important. This temperature was 1100 degrees centigrade. The pressure 5, 10, 15, 20, 25, 30. Just to give you an idea, this is 100 kilometers approximately. 100 kilometers. And you know the depth of the Morovicic discontinuity varies between say 35 kilobars. So that means 35 kilobars means roughly this would be a good average of crust and the mantle. Good average of the crust of the mantle, because the Morovicic discontinuity occurs at around 36 kilobars. If it, 36 kilometers. If it's 36 kilometers, then you divide it by 3.3, roughly 11, 12 kilobars this would be the boundary, this will be Moho, roughly Moho. And he took a quartz tholite, which is common on the ocean floor. You know, they undergo subduction, etc. And here on the left hand there is a mineral composition. This is the abundance of mineral percentage. So he took a rock of this percentage. What is the percentage? Plagioclase is roughly 50%. Orthopyroxene 50 to 70, roughly 20%. Clinopyroxene 70 to 90, roughly 20%. Rest is ilmenite, rutile, quartz, etc. They make the rest of the 10%. So that is what. So he had, apart from that, he had ilmenite and quartz. This made up the remaining thing. And if you go to the other extreme here, you will see that clinopyroxene here is roughly about 30-35%. Garnet is 50% roughly here, and quartz is 10%. So it's roughly 90%. This is garnet, clinopyroxene, quartz. So this is the eclogite facies assemblage. So this is the eclogite facies assemblage. This is the gabbro-granulite facies assemblage. This is how he took at different pressure mineral assemblages that crystallized in his experimental runs at 1100 degrees centigrade and different pressures. He did this experiment. This is quartz tholite. He did it for about 30 to 40 different types of rocks in his laboratory. And for each of them he presented a data. What is here? You see, you start with ilmenite here, gives to rutile, remember? Garnet formation, rutile. Then you start with quartz, remember? All this garnet producing reaction produced quartz. So the quartz volume percent increased. This is clinopyroxene, but it is augite in composition. That means CMgSi2O6. Augite in composition. But when you are here, it is omphacite in composition. That means sodic clinopyroxene in composition. Orthopyroxene is stable till here, and after that you have garnet. So now you can see, if I draw another line here, this is where the garnet comes into play. As you move high pressure, there is no garnet. You get clinopyroxene, augite, plagioclase. This is anorthite rich. And as we move, the plagioclase content decrease. We talked about it. And the plagioclase become more albite rich. But if you take this line, what is present? You have plagioclase, orthopyroxene, a little bit of garnet appears. So you are into the high pressure zone. And then you have clinopyroxene and quartz. But as you move up pressure, then first you lose is orthopyroxene. You lose orthopyroxene. So on this side, you don't have orthopyroxene. On the right of this line, you don't have orthopyroxene. What you have plagioclase, which is albitic. You have garnet. You have clinopyroxene. You have quartz. No orthopyroxene. So your granulite facies stops here. Left of this pressure is a granulite facies, and right of this is clinopyroxene garnet subfacies, because orthopyroxene has now. And if you go even higher pressure, then here plagioclase also goes out. So this is your eclogite facies assemblage. No plagioclase. Clinopyroxene, garnet, quartz. Before that, you have garnet, clinopyroxene, plagioclase, quartz at lower pressure. At even lower pressure, you have orthopyroxene at lower pressure. So that is very important. So from this side, low pressure to high pressure, we have gone from intermediate pressure pyroxenes to garnet free, then to high pressure granulites, garnet bearing to pyroxene plus plagioclase, then we lost orthopyroxene, and then we lost plagioclase, and then we are in the eclogite phases. This is quartz tholite because it's very, very common all over the Earth's surface. So this is the transformation that occurs. This is the transformation that occurs over all the rocks. So what this shows was a very, very important feature. So this is granulite facies and this is eclogite facies. What is the difference? The difference is roughly about 5 kilobars for this composition. 5 kilobars. That means if there was a gabbro at the top and eclogitic mantle below, then this transition would have required 5 kilobars, meaning about 18 kilometers depth would be required for the transition from granulite gabbro to eclogite. 15 kilometers for a quartz tholite, which is a very common rock in the ocean floor. So the transition from granulite to pyroxene plagioclase assemblages to garnet bearing assemblages, that is about 5 kilobar pressure, meaning about 18 kilometers. So if you say that, okay, my morovisic discontinuity is a transition from low pressure granulite to eclogite, then that morovisic discontinuity should be 18 kilometers wide. At present, this is shown to be less than 300 meters. The geophysical waves, they show less than 300 meters. So this gabbro-eclogite transition as the origin for moho is completely wrong. There were other evidences that crept in. I will give you a summary diagram. So this is more about I'm relating my theoretical reactions with the experimental data. Ringwood and Green has many papers, so those who are interested, you can work with it. There is one important thing before, if any of you have read the papers. He did not use silicon in his experiment, he used germanium, because germanium was far more reactive. So he used germanium, which is very close to silicon in chemical characters. So his experiment was based on germanium, not silicon. But that does not change any part of the story. And now I will give a diagram which is a very simplified diagram, but I think it should be given to you. You should see it. All parts of it may not be correct, but that's about it. You have to take it. So this is a summary diagram. Here you can see I have only shown you few, but these are different types of basalts and gabbros that he could lay his hands on. Quartz thoriites, olivine thoriites, even he has Apollo 11 basalt. He used that also as his experimental run. Then he used gabbro and orthosite, rhyodacite, all conceivable rocks that you see in the oceanic crust. the idea is that it will turn into eclogites. So he found out the transition at 1100 degrees centigrade, the transition from pyroxene granulite, low pressure granulite, crustal granulites or gabbros, to garnet bearing granulites to eclogites. And you can see here at this point, the difference is, can you see the difference in pressure? The difference in pressure is 30 to roughly 10 kilobars. That means 20 kilobars. 20 kilobars means the transition to gabbro or pyroxene granulites to eclogites would require about 20 kilobars. 20 kilobars means more than 65 kilometer depth. Impossibility for a moho, because moho is almost a razor sharp boundary, an absolute razor sharp boundary. But the smallest that you get is for Apollo 11 basalt, where the pressure drop is less than 2 kilobars. 2 kilobars means roughly 6.5 kilometers. So the smallest transition was taken by an Apollo 11 basalt. But overall you can see the large amount of depth that is required for transforming gabbro to eclogite, and it is impossible to do it across the board of basic discontinuity. So he was the first person who said, you just can't have a phase change boundary as the moho. It is now known that the moho is not eclogite. It is actually ultramafic peridotites in which there are eclogites occurring as pods like in a cake or something. The proportion of eclogites is to peridotites is roughly in the proportion of 75% peridotite, which he called as a peridotite, and 25% basalt. You know that this is called the pyrolite model of Anderson and Green. 75-25. This 25% basalt is because the mantle only contains 25% eclogite. 75% is a peridotite. That is why 1:3 is the ratio comes from this pyrolite model, because the mantle below the Mohoro basic discontinuity contains 25% eclogites, not basalts. Eclogite. But since eclogites are chemically similar to basalts, eclogites and eclogite facies, these are two different things. Eclogite facies is a metamorphic PT condition over which all rocks stabilize into eclogite facies assemblage. But an eclogite per se is a basalt metamorphosed at eclogite facies condition. A basalt metamorphosed at eclogite facies condition is called an eclogite. An eclogite facies is the PT condition where any rock crystallizes at that pressure temperature condition is called eclogite facies rocks. So his 25% basalt comes from the fact that you only 25% of the upper mantle contain eclogite. How did they bring it? How did they come to this ratio 75:25? You know, they looked at kimberlite pipes, they looked at diatreme pipes, and if these pipes were coming from greater depth, they were sampling the upper mantle. And they tried to find out what is the proportion of the xenoliths of peridotites and eclogites. And they found the ratio hovered around 75:25. So he said, then what is the composition of the upper mantle? It was 75% peridotite, 25% eclogite. So he coined that as pyrolite. So the emphasis of this was to disprove completely that the monovasic discontinuity is an isochemical phase transition boundary is wrong. That the monovasic discontinuity is essentially represent a chemically stratified earth, where above you might have the SEMA, but below you have an ultramafic rock with 75% peridotite and 25% eclogite, which is called the pyrolite. Thank you.